The Earth is hot, hot enough to melt your face off if you happen to wander onto it without any protection. A thick atmosphere of carbon dioxide, nitrogen, and methane surrounds it, but there's no oxygen. It's not breathable. Volcanic eruptions spew gases and molten rock onto the surface, which is mostly covered with magma. Meteorites streak across the sky, slamming into the molten crust and causing massive earthquakes. Welcome to Earth 4.5 billion years ago. This was the Earth before life, before water, before continents, and certainly before pizzas. It was a hot mess, really. In the last episode, we saw how the Earth formed when two pieces of debris from the formation of the solar system collided and stuck together. The Earth wasn't alone. The solar system was bustling with activity. Mercury, Venus, Mars, Jupiter, and Saturn were all forming at the same time. But Earth had something that the others didn't: abundant water. That made it special, although not in a good way. Imagine standing on a beach as a tidal wave twice the height of Everest crashes down on you. Now imagine that happening every few hours. That was life on Earth. Earth was part of a cosmic collision zone. It was constantly bombarded by leftover space rocks that hadn't formed into planets or been swept away by the solar winds. Some were small and some were huge. One of them was called Theia. It was about the size of Mars, and it crashed into Earth, probably near the equator. Not surprisingly, this event was pretty apocalyptic. Theia's impact heated the Earth to temperatures higher than the surface of the Sun. Most of the planet's water and lighter elements boiled away into space. Theia itself was vaporized, but not before mixing its material with that of Earth. Much of Theia's mantle, along with some of Earth's own mantle, formed a layer between the core and the crust. This layer is the source of Earth's magnetic field, which shields us from harmful radiation and makes life possible. So the giant space smash that devastated Earth also created conditions that would later allow life to flourish. But don't get too excited just yet. Even after Theia left, Earth continued to be barraged by smaller space rocks. The biggest were the meteorites, chunks of rock that ranged in size from a house to a mountain. They crashed into Earth at 25 kilometers per second, which is 90,000 kilometers per hour. These impacts were so powerful they could shatter solid rock, and at first the Earth was unable to hold on to its new water. Every time a meteorite hit, it sent up a plume of vaporized rock and water that disappeared into space. But over time, the bombardments became less frequent, and Earth's gravity began to pull more water back down to the surface. Within a few million years, it was completely covered in ocean. Now the scene is set. It's still hot, stormy, and volcanic, but the water creates a cooling effect. There are also other things floating around in the atmosphere besides gas. Now that the temperature is dropping, it's raining rocks. Solid particles of dust and smoke condense out of the atmosphere and fall as rain. Rain, hail, asteroid, baby. No joke. These falling objects are often called meteorites, but technically a meteorite is the chunk of rock left behind after an asteroid strikes the Earth. Sometimes these space rocks contain organic chemicals such as amino acids, which are the building blocks of proteins and are essential to life. One such meteorite landed in Australia in 1969 and turned out to be the richest source of amino acids ever found. It was named the Murchison meteorite, and scientists believe it came from a small asteroid that had been knocked out of orbit by a wayward planet. In addition to meteorites, frozen comets are crashing into Earth too. They come in from outer space and deliver volleys of water, carbon dioxide, and ammonia. Some scientists think life on Earth began thanks to these comet deliveries. If that's true, we can thank comets for bringing water and organic molecules to our planet. But they were also responsible for some serious devastation. About 3.8 billion years ago, Earth was struck by a giant comet. Fragments rained down on the planet for months. The impact released huge amounts of energy, perhaps 1 million times greater than the energy of the atomic bomb dropped on Hiroshima. This comet was so big it was visible from Earth, and it left a scar on the Moon that we can still see today. It's called Tycho, and it's 120 kilometers wide. After the comet struck, it created a new mineral called tektite. These glassy beads were scattered around the world and contained tiny bubbles of ancient gas. The gas bubbles can tell us what the atmosphere was like millions of years ago, and they show that the composition of the atmosphere changed after the comet's impact. More carbon dioxide and less nitrogen and methane. Scientists have discovered evidence of similar comet impacts all over the world and across the solar system. They leave behind layers of sediment that are rich in carbon-14, an isotope of carbon that's produced in the upper atmosphere when nitrogen is hit by cosmic rays. These layers go back hundreds of millions of years and help scientists identify the time periods when comets slammed into Earth. But comets weren't the only thing stirring life into the oceans. Underneath the waves, chemistry was getting into gear. The first step was creating a soup. As water vapor condensed and fell as rain, many minerals leached into it from the rocks. Minerals are composed of elements such as aluminum, magnesium, and calcium. When mixed with water, they form ions, electrically charged atoms that can conduct electricity. This electric conductivity is a property of life. All living things have the ability to conduct electricity because they use charged particles called ions to store and transmit energy. But the electrical currents in the oceans ran backward. Instead of being used by living things, the current flowed from the rocks into the oceans. Scientists call this process autocatalysis. The minerals sparked a chain reaction that led to the creation of amino acids, sugars, nucleotides, and other molecules that are the basis of life. The Earth was on its way to becoming habitable. However, the energy for this chemical activity came from the sun. Photosynthesis, the process by which green things convert sunlight into chemical energy, was still millions of years away. During those early days, the oceans glowed with bioluminescence. Bioluminescence is a chemical reaction that produces light. You can see it in fireflies, jellyfish, and deep sea fish. On Earth, the glow came from hydrogen sulfide that was seeping out of the seafloor. The stuff reacted with oxygen in the presence of iron and zinc to produce light. This glow illuminated the bizarre creatures that swam in the seas. What kinds of life forms existed before the first multicellular organism, before fish, dinosaurs, giraffes, humans? To find out, scientists study stromatolites. These structures are formed by layers of bacteria and sediment. They resemble modern coral reefs, but they're much older. Stromatolites can be found all over the world and date back billions of years. Some of the oldest ones are almost 3.5 billion years old and were found in Greenland. They're called apatite and are made of calcium phosphate instead of calcium carbonate. Apatite contains more information than other stromatolites because it preserves chemical signatures of the environment in which it formed. Analysis of these signatures reveals that Earth's early oceans were salty, alkaline, and full of organic matter. One theory is that the bacteria inside the stromatolites absorbed carbon dioxide from the atmosphere. They extracted carbon from that and combined it with hydrogen sulfide to make organic compounds. Another theory proposes that the bacteria farmed methane. They captured methane as it seeped out of the seafloor and used it as food. Regardless of how they acquired their energy, these bacteria populated the oceans and thrived for millions of years. Eventually, though, something happened that decimated the stromatolite population. A mass extinction killed off 90% of the species on Earth. One theory blames the oxygen revolution. Photosynthetic bacteria were producing oxygen as a waste product. Oxygen is reactive and combined with iron and other minerals to form new compounds. The oceans lost their conductivity and the chemical activity that powered early life came to a halt. But not all life was destroyed. Some bacteria adapted to the changing conditions and learned to use oxygen to generate energy. Others went into hiding. They retreated into the seafloor where they've remained for billions of years, surviving in the same way that they did before the Great Oxidation Event. They're called chemoautotrophs, and they use hydrogen sulfide, sulfur, iron, or nitrogen as energy. Now the Earth is ready for bigger things. The stage is set for the first complex organisms. In the next episode, we'll watch as cells form and life explodes.